perspectives. Right? One is pricing, something which you have probably already encountered in some of the lectures. One is, of course, asset management, and there is question of risk management. So personally, these are the three main things that I teach and work on, in addition to, of course, computational finance, both from the numerical PDA perspective, as well as your Monte Carlo simulation perspective. But if you speak to anyone who works in mathematical finance, you will see that the main thing that they focus on is, one is pricing, and the other is risk management. And a portfolio optimization is something that pervades both of these areas. So there is a lot of overlap within different areas. But what I will talk about today mainly is going to be on portfolio optimization and its fallouts. And this will be the classical approach to portfolio theory, or what is called the modern portfolio theory. Even though it has been almost 70 years since this was first established, but it is called the modern portfolio theory from the point of view that this was the first mathematical framework which gave a very objective way of driving investment decisions as compared to the previously adopted approach, which was mostly driven by sentiments and was mostly ad hoc in nature. So I'll actually go through this lecture from scratch because I presume that a lot of our audience today would not have been exposed to this kind of things at any point. So I'll go slowly. Please feel free to stop me at any point if you have any difficulties. So I'll start off with trying to motivate as to why we need to talk about portfolio theory. So first of all, I'll talk about investment choices. You see, at the end of the day, we all have to make the investment decisions, some form or the other, and this is something we cannot avoid. So when one makes an investment decision, the initial outlay of capital is known. So that means the initial amount of money that you are putting in that investment obviously is known, because that is the amount of money you have, and obviously you know how much money is going to get investment. However, the return may be known or unknown. But suppose that you make an investment for a certain period of time, say 1 year. While you know what is the amount of money that you have invested now, that is a deterministic quantity, what you are going to get back at the end of 1 year, it may be known or unknown. So there are both the possibilities. And now let us look at what are the circumstances under which this return may be known or unknown. And of course, I'll quantify what return is later on. So it is going to be known in case of bonds, money market accounts, fixed deposits. So what happens is, suppose you go to the bank and you get a fixed deposit, and bonds are basically very much similar to fixed deposits, or money market account is very much similar to some sort of a savings account. So you suppose you put in 100 rupees. So of course, and the bank tells you, okay, you can take a fixed deposit of 1 year, and we will give you an interest rate of 10% per annum, calculated once a year. So right at the beginning itself that if you invest an amount of 100 rupees at 10%, then you know that at the end of 1 year, the bank is going to give you back an amount of 110, and then there is no ambiguity regarding that. So now, however, if instead of that, you go into a stock or derivatives or so on, then it's unknown, because if you invest 100 rupees in purchasing a stock today, you really don't know sitting today what is going to be the value of the stock at the end of 1 year. So if it becomes, if you get 110 rupees, then you are getting a 10% return. If it becomes 90 rupees, that means you are expecting a loss of 10% or a minus 10% return, and so on. So this is what I meant by that the return that you have may be known or unknown. So typically when we talk about a known return, we'll refer to that as a case where we are talking about bonds. And in case of unknown returns, we'll keep at the back of our mind that we are talking about a stock or derivatives, but typically we will refer to this as a stock. And this notion of investment in a bond or stock will be essentially our choices for all the illustrative cases that will follow for the remainder of my lecture today. So I use the term portfolio optimization. So first of all, I need to talk about what is a portfolio. So a portfolio is a collection of assets A1, A2, AN in a given proportion. And formally, we define portfolio to be an ordered n tuple of real numbers, theta, given as theta 1, theta 2, theta n, where theta I is the number of units of the asset AI. So suppose I have assets A1, A2 all the way to AN. So think of those assets as being some n number of stocks. And then if you have theta 1 number of stocks that you have purchased for the first stock A1, if you have theta 2 number of stocks that you have purchased for the second stock, which I identify as asset A2 and so on. So here theta 1, theta 2 all the way to theta n, these are some real numbers which indicate the number of units of the corresponding ith asset, which intuitively for the purpose of our discussion will consider these assets A1 through AN to be either stocks or bonds, but it need not be just restricted to these two. You can basically include any other kind of investment. Now, what is the physical manifestation of a portfolio? A physical manifestation of a portfolio in our days would be what? We put some money in fixed deposits, NSCs, and so on, buy some stocks. Today, this might be your, say, your or online banking account, your mutual fund, your demat. In fact, mutual fund is basically nothing but a portfolio that is managed by fund managers. Now, in my previous narrative, I have defined the portfolio essentially to be a vector of real numbers, theta 1 to theta n. And these are the number of units. Now, as I said that these are real numbers. So naturally, it gives rise to the question that if they are real numbers, can they be negative? And the answer to this is yes, theta i's can be negative. Now, if the theta I is negative, then we say that the portfolio has a short position in that asset. So you must have done there a little bit of discussion on short selling. So if theta I is negative, that means you have a short position on the asset. So if the asset is a stock, this will mean you are short selling a stock. That means you are borrowing somebody else's stock. So that means since you owe them a stock, so that that means that you are actually effectively owning a negative number of stock, or you have a short or a short put or a call option. For example, if your asset is a bond, then theta I negative would mean that you are not actually getting a fixed deposit or buying a bond, but you are actually borrowing money. So what happens when you buy a fixed deposit? That means you are own or a bond. That means you are owning a certain unit of bond. That means you have actually lent money to the bank. So if on the other hand, if your number of units of the bond is negative, that means you are actually borrowing from the bank. So this is a very critical observation that theta I negative, its interpretation is equivalent to short selling of a stock or borrowing money in case of a stock and in case of a bond. Okay, in an analogous manner, theta I can also be positive, and if theta I is positive, then it indicates a long position. So in case of a stock, it means that you are the owner of a stock and that you have actually purchased the stock, and or it could be a long position in a put or a call option. And in case of a bond, this means that you are the ownership of a bond, or that means you have put money and got a fixed deposit. Okay. Now, this is sort of very nice, no problem from a mathematical point of view. Okay, I'm talking about that a portfolio is just a vector where the entries of the vector gives us the exact number of assets that we have in our position, either a long or a short position, depending whether the entry theta I is positive or entry theta I is negative, respectively. Now, let us come to modern portfolio theory. So, in case of modern portfolio theory, there are what are the characteristics of a portfolio? See, at the end of the portfolio, at the end of the day, the driver of a portfolio involves two characteristic parameters. One is the return, and other is the risk. So, prior to this modern portfolio theory, what you had was that it was done in a slightly haphazard fashion, and people did not recognize the fact that usually higher return is accompanied by higher amount of risk. So more risk, if you are getting higher return, then obviously it is associated with the investment that is more risky. and vice versa. So the modern portfolio theory at a very basic and intuitive level, it is an area of finance that seeks to achieve one of the following goals. So I will say enumerate the two goals that is there. One is that if you are given a certain level of risk of a portfolio, then you say that, okay, I want to invest in a portfolio. That means I want to make a choice of this theta 1, theta 2, all the way to theta n, such that I have a fixed level of risk, and there could be many combination of these theta i's which could give me that level of risk. And among this combination, I want to find that combination which will give me the maximum value of return. Or alternatively, if I fix a given level of return, then at that given level of return, I could have many combinations of theta i's or equivalently many different portfolios. And since I'm looking at a fixed level of return, that means what I would want is at that fixed level of return, I want to choose that combination of portfolio or this combination of theta i's for which my risk is going to be minimal. Now here I have used the term return and risk in an intuitive sense, but I have not quantified it, but I'm going to soon quantify and precisely define what I mean by return and risk. And the other alternative is that, I mean, modern portfolio theory, I have stated, enumerated these two objectives, or an alternative objective would be simply minimize the risk of the portfolio. That I take up different combinations of portfolio, minimize the risk, which I will define soon, and then find out for what combinations of theta 1 to theta n will I basically get the minimum amount of risk. Okay, now I have mentioned that this modern portfolio theory, which incidentally was due to a 1952 paper by Harry Markovians, which eventually won him the Nobel Prize several decades later. And the two pillars of the modern portfolio theory due to Markovians are the return and risk, which I have mentioned in the previous slide. So accordingly, let us talk about what is the return of an asset. So when we talk of the return of the asset, we first identify the asset. So we take a generic asset, say AI, and suppose that I'm looking at a time window of 0 to capital T. Suppose that I'm looking at a period starting today, which I identify as time 0, and ending at a future time period of time t equal to capital T. So suppose that the value of the asset today is V subscript I comma 0. So V of I is the value of the ith asset, and comma 0 will indicate that is the value of the ith asset at time t equal to 0. And using this nomenclature, I can immediately define the value of the ith asset at time capital T to be V I subscript I comma capital T. So the return will then be determined by what? The return will be given by VI0, that is the initial amount, into 1 plus RI, which is the return of the ith asset. And this, if it is the return, then by definition, VI0 into 1 plus RI must be equal to the value of the asset I at time capital T. Or solving this, you can get the return to be VIT minus VI0 over VI0, which is a standard notion of return, that the final price of the asset minus the initial price of the asset divided by the initial price of the asset. Now, obviously, as you can see that this is basically a ratio, and if you multiply this by percentage by 100, then you get the return in terms of percentage. So if RI turns out to be 0.05, then you say that the return is 0.05 into 100, which is equal to 5%. Now, remember that at the beginning, what I had said that the initial investment VI0 on this asset is a known quantity, because you know what is the value of the asset at time t equal to 0. But sitting at time t equal to 0, you may know what is VIT or you may not know. So if your asset AI is a bond, then of course you will know what is VIT. But if your asset is unknown, is a risky asset like a stock, then of course VIT is uncertain. So this is going to be a random variable. Now, VI0 is a deterministic quantity, is not a random variable, but VIT, it can be a random variable or it may not be a random variable. Now, if it is not a random variable like a bond, then of course there is nothing interesting in it, because you know right at the beginning what is going to happen at the end of the period time t equal to capital T. So there is nothing interesting about it. There is no uncertainty as far as your returns are concerned. But if it is a stock, there is uncertainty, in which case VIT is going to be a random variable. Now, if VIT is a random variable, so VIT minus VI0 is going to be a random variable, and VIT minus VI0 over VI0 is going to be random variable. So when I talk about the return Ri, in this sense, it is not going to be a fixed quantity, but it is going to be a random variable. So once I say that this is a random variable, I cannot then just restrict myself to talking about the return Ri, but then I need to calculate what is going to be the expected value of this return. So this brings me to the notion of what is the expected value of return. So the expected return of an asset, as I said, since VIT is a random variable, which results in Ri being a random variable, so the expected return will be the expected value of Ri, and it is customary to use the notation μi for the expected random variable. So now, so this is so I know what is the return of an asset now, and I know what is the expected return of an asset. Now let us come to risk. Remember that we are talking about two pillars of portfolio theory, return and risk. So now let's come to the risk of an asset. Now the risk of an asset, in order to talk about the risk of an asset, we first need to talk about the variance of the return of an asset AI, and this variance will be given by var of Ri, and I will denote this by sigma I square. And the risk of an asset AI is given by the variance sigma I square. So by definition, the risk of an asset is the variance of the return Ri, and the square root of this, which is sigma I, is the standard deviation. So in portfolio theory, depending on the context, we will interchangeably make use of sigma I square or equivalently sigma I as the measure of risk as the situation arises. So both of them are used as a measure of risk. Now, the point that I want to note here is that why am I choosing this as a measure of risk? See, risk means what? Where does the risk for your investment come from? The source of risk for your investment comes from the variability in the return. So suppose that you are having a return for 5 years, and the return for each of those years is always 10%. That means it's a bond. So the variance is going to be 0, so there is no risk. But if you're investing in a stock and the returns are minus 10%, plus 20%, plus 30%, minus 20%, and so on, so it keeps jumping. So that means its variance is going to be high. So the more this unpredictable behavior of the returns of the asset, the more is going to be its variance. And unpredictability is, in this context, is synonymous with risk. And that is the reason why we consider the variance, which is effectively the same thing as a standard deviation in principle, because one is just a square of the other, as the natural choice of risk. Now, having said so, this was the natural choice of risk that was put forth by Markovians, but subsequently there has been many different definitions of measures of risk, things like semi-deviations, value at risk, conditional value at risk, and so on. So there are, please don't sort of, before somebody jumps up and says why only this choice, this is not the only choice, but this was the choice which was a natural choice that was made for when the foundations of modern portfolio theory was laid, but subsequently much more sophisticated versions from mathematical point of view of measures of risk have come into existence. But having said so, given this easy understandability of usage of the expected value and variance as a measure of return and risk, its popularity even after 70 years of development of the modern portfolio theory, the popularity remains as strong as it ever was, because it makes things easier to understand for the end user. Okay, so what have I done so far? So far, what I have done is I have talked about the return and risk of a single asset. But remember, we are not talking about single asset. We are talking about investment in several assets. So at this point, I want to make a shift in terms of definition of the portfolio and introduce the notion of asset weights in a portfolio of n number of assets. So it is customary to measure the amount of an asset within a portfolio by its percentage. So when we typically define a portfolio, we don't actually use theta 1, theta 2 number, but instead we use weights, which indicates the percentage of or the proportion of the total money that you have put in that particular asset. So this means that suppose you have 10,000 rupees and my portfolio is given in terms of weights. Yes.
Sir, is risk is included? The accident like fire, all the risk factors are included.
No. You are going in a completely different direction. Fire risk here purely means the risk that is emanating from the return of the assets.
Oh, okay.
Right. So you know the return of the assets may get influenced negatively by a fire happening. If a fire happens, that means the company cannot pay your dividends on time. The company is will have business disruption that is going to in turn result in a reduction of your value of the stock. So that means your return is likely to end up being negative. So directly in this, I am not including those kind of external factors, but indirectly that is included in terms of the impact it is going to have on the return of the assets. Okay, so now that so suppose that we now consider a portfolio where the number of units of the ith asset is say Ni. So instead of theta, I just said that okay, for the ith assets, I have purchased Ni number of assets. So then what is the total for the ith asset? What is the amount of money that I have invested at time t equal to 0? It is going to be the value of the ith asset vi0 multiplied by the number of assets. So that means that is the total money that I have invested in the ith asset at time t equal to 0. Now, so this is the investment NIVI0 that I make, the absolute amount of money that I have put in my ith asset. So if I sum all of this up over all n number of assets, that is going to be the overall portfolio in the whole asset, or in the overall investment in the whole portfolio. Then how do I define my weight? So the weight of the ith asset will be given by the amount of money that is invested in the ith asset, which is VI0 into NI, divided by the total amount of money that is invested in all the assets. So investment in only the ith asset divided by the total investment. So that means you get, and that will be give you the fraction of money that is invested in the ith asset as compared to the total amount of money invested in the whole portfolio. And that is going to be what is known as the weight of the ith asset. Now, if we sum up this Wi from I equal to 1 to m, what is this going to be? It is going to be summation of this term here. So then both the numerator and denominator will become summation of Ni0 Vi0, which cancels out and adds up to 1. So all the weights are add up to 1. So these Wi's are nothing but the fraction of your total investment that has been put in the ith asset. So from this point of view, from this point onwards, we will not look at a portfolio in terms of theta 1, theta 2 all the way to theta n, but we will talk only in terms of weights, which is given as W1, W2 all the way to Wn, such that the sum of all these Wi's is going to be equal to 1. Okay, now that I have defined what is a weight, it is time to again come back to the discussion of a return of an asset and risk of an asset individually. And we have already defined what is the return of an asset. We have already defined what is the risk of an asset. And now we want to, in case of an individual asset, and now we want to extend it into a portfolio of n number of assets. Now, suppose that, so what is the number of units of each asset? So remember the following: the number of units of each assets, the number theta I of each asset is given by theta I. So what I do here is, remember, so here I have put Ni. So actually I should have put Ni here. So please view this theta I as Ni. So what I have done here is, what you do is, Here, what is going to be your Ni or equivalently theta I? This is going to be Wi into this summation divided by Vi0, which is what I have written here. Theta I is equal to Wi into summation over Vi0. So that is the number of units of each of the assets. Okay, now then this particular portfolio, so what is going to be the overall return of the portfolio? Overall return of the portfolio is simply going to be the value of the portfolio V of t minus V of 0. Remember that V of 0 is suppose the initial amount that you invest in the portfolio, and your value of the portfolio or time capital T is going to be V of t over V0. Now this V of V0 is nothing but summation of theta I Vi0, right? Because that is the amount of money that you have invested in the portfolio initially, and V of t is going to be nothing but summation theta I Vi of t. So what I have done here, so once you have this formulation, so you have theta I Vi of t minus V0 over V0. Then if you now replace this value of theta I here with these values here, and you do a little bit of manipulation, then you will arrive at this relation summation of Wi Ri I is equal to 1 to n. So that means if we have a portfolio whose weights in each of the assets A1 through AN are given by W1 through Wn, then the return of the portfolio R will be given by the weighted sum, that is summation of all the returns multiplied by their corresponding weights. So for each individual asset, the return is Ri, and then once you put all the assets together in a portfolio, then the return R of the portfolio is going to be given by summation of Wi into the return of each of the individual assets. So it can be stated that the rate of return of a portfolio, or simply the return. So sometimes we talk in terms of rate of return. So this essentially means the same thing, is simply the weighted sum of the rate of return of each asset. So this is what I have mentioned. The rate of portfolio is going to be weighted sum of the returns of each individual asset. So what I have done here is, starting off with the return of each individual asset, I have moved on to what is the return of the portfolio as a whole. So since this is a random variable, remember that these Wi's are of course fixed quantity, because Wi is determined making use of your investment amount at the initial time, which is a known quantity. But remember that Ri individually, each of them is a random variable. So a linear combination of this random variable, which is given by R, is also going to be a random variable, and the random variable reflecting the return of the portfolio. So then now we need to talk about what is the return and risk of the portfolio as a whole, once I have obtained the return in terms of the returns of individual assets. So as I said, the next natural step would be to talk about what is going to be the expected return and what is going to be the risk. So what is going to be the expected return of a portfolio? The expected return of a portfolio is going to be the expected value of R, which is the expected value of this summation. So this is going to be expected value of summation Wi Ri I equal to 1 to n. And I denote this by mu. Now expected value of summation Wi Ri, this we can make use of the linearity property of expectation and write it as summation of Wi into expected value of Ri. Remember, Wi is not a random variable, but only Ri is a random variable. So this can come out. And what is expected value of Ri? In our previous notation, this was mu y. So I can write the expected return mu of the portfolio is going to be summation of Wi into mu y, which is the expected return of each individual asset. Okay, so now we have this quantity, this expected return. So next we talk about the risk of a portfolio, and risk of a portfolio or a portfolio variance. So that means it's time for me to talk about the risk of the risk in terms of the whole portfolio. So what is this going to be? This is going to be nothing but variance of R, which is going to be the variance of the summation Wi Ri. So this is going to be sigma square is equal to variance of summation Wi Ri, And then you can make use of the definition of a variance of a linear combination. So remember, what is variance of ax plus by? It is a square into variance of x plus b square into variance of y plus twice ab into covariance of x and y. So the same formula, when extended to n number of random variables, we get this to a double summation of wi wj into covariance of ri rj. And this covariance of Ri Rj, I will denote this by sigma subscript Ij. So this becomes, so I know what is Wi Wj. Remember, Ri and Rj, these are random variables which take certain values. So I can calculate their covariance, which I shall denote by sigma Ij. And then Wi and Wj are known quantities. So using this formula, I can calculate what is going to be the variance of the portfolio as a whole. So what I have done so far, we have done is that we have looked at what is the expected return of an individual asset and risk of an individual asset, and extended that in case of the expected return of the portfolio as a whole, as well as the corresponding risk of the portfolio as a whole. Now, once we have moved, once we have precisely put in place what is return and risk, both individually for the assets as well as a portfolio of assets, I want to briefly deviate a little bit and talk about systematic and unsystematic risk. Now, what is systematic risk? So systematic risk, as the name suggests, is something that is associated with the system. And the system in this case is the market as a whole. So systematic risk is the risk associated with the macroeconomic force of the market as a whole. So basically, there are certain common market forces which can influence or which are risky, which pose a risk to the return of all the assets in the market. And those factors are called systematic risk. And I will mathematically talk about it after a few slides. And there is something called the unsystematic risk. And this is the risk to that particular return of that asset resulting from some characteristic of the assets itself or the group of assets. So for example, if there is a interest rate increase, that is something that might affect, that is obviously going to affect all the companies. But suppose that it is something like airline industry. Once something like COVID happens, obviously an airline industry is going to be hit much more than say healthcare industry. So that is something that is localized, to certain specific sectors. Or suddenly, if there is a change in the energy policy and the government cuts down on pollution and brings in new laws, then the group of companies that are going to be most affected are going to be things like oil companies or coal companies and so on. So the factors which affect everybody, that is called systematic risk, and the factors which affect a certain group or certain individual assets as far as the returns are concerned, those are called unsystematic risk. And the difference between this is unsystematic risk can be diversified away. So if you invest, if you don't restrict yourself only to the assets, 2 or 3 assets, but large number of assets, then you can reduce the unsystematic risk. But systematic risk you cannot get rid of. Intuitively, you can see that this makes sense because systematic risk, that is happening something globally which affects all the assets. So obviously you cannot you cannot do much, because even if you diversify and invest in large number of different assets, all those assets in turn are anyway going to be affected by the macroeconomic factors. So systematic risk cannot be gotten rid of by just adopting a strategy of diversification. And by diversification, I mean here that not restricting yourself to investment in only a few assets, but to a reasonably large number of assets. So that means that don't invest in only 1 or 2 assets, but maybe 8 to 10 different assets is what you can invest in. So that means you have diversified your position. Okay, now let us start talking about, and I talked about weights, all right? And the problem with this is that when I talk about weights, weights basically, what does weight mean? Weight basically is the same thing as equivalent to the number of assets you should buy. So so here, for example, if you remember, if you have to determine what is your going to be at weights. or equivalent, you have to determine what is the number of assets you want to buy. So if you want to buy theta number of assets, then it is dependent on your WI number of the weights. So this means that you have to figure out what is going to be the best combination of weights W1 to Wn, which fulfills your objectives as an investor. Now, what do I mean by fulfills the objectives as an investor? So for this, I want you to recall my previous statement that we can view the investment strategy being driven by the consideration that either you fix the risk that you want to take and you maximize the return, or you fix the return and then you minimize the risk. Now, in order to have a greater clarity on exactly how this can be accomplished using any optimization approach, we consider a scenario where our portfolio has only two assets. Okay, so suppose that we have only two assets, A1 and A2, and with the respective weights of W1 and W2. Now, as you can see that obviously W1 plus W2 is going to be equal to 1. Then what is going to be the expected return of this portfolio? So remember that the expected return of the portfolio is W1 mu1 plus W2 mu2. So I'm just making use of this formula. So at this stage, I'm just going to make use of this formula for the expected return and this for the variance. So the expected return is given by this formula where mu1 and mu2 are the expected returns for the first and the second asset. And likewise, the risk is given by sigma square is equal to W1 square sigma 1 square plus W2 square sigma 2 square plus 2s W1 W2 sigma 1 2. So you can easily get this from this formula by letting I is equal to 1 to n, j is equal to 1 to n. So when both I and j are 1, then you will get W1 square. When both I and j are 2, you will get W2 square. And when I is 1 and j is 2, or I is 2 and j is 1, you will get W1, W2. So that becomes twice W1, W2 into sigma 1, 2. And remember that sigma 1, 2 is sigma 2, 1. Because covariance of two random variables x and y is the same as the covariance of y and x. So the risk for this portfolio is given by this formula, which can be written as, so instead of writing sigma 1 and 2, remember sigma 1, 2 is covariance. Now remember the correlation coefficient by definition is given by rho. There is a notation for correlation coefficient, and that is given by covariance, which is this sigma 1, 2 divided by standard deviation of the first random variable, that is sigma 1, and second random variable, that is sigma 2. So what I'm doing here is I'm just bringing this into the picture, whereby it's the same thing that I'm rewriting in the next line, except that I'm writing now this sigma 1, 2 in terms of the correlation coefficient and individual standard deviation sigma 1 and sigma 2. Now remember that one of the properties of the correlation coefficient is that the correlation coefficient, the absolute value of that is less than or equal to 1, or that it lies between -1 and +1. Okay, now that we have looked at this two asset portfolio and we have the expected return and risk, let us now start determining what is going to be the best choice of W1 and W2 with a certain objective in mind. So we can take one objective. So let us first just look at a simple objective where I want amongst all combinations of W1 and W2, I want that combination which gives me the minimum risk. So that means I want that combination of W1 and W2 so that, see, remember sigma 1, sigma 2, rho 1 to sigma 1, sigma 2, these are fixed quantities. Once you have decided what your assets A1 and A2 are going to be, these are going to be fixed quantities. Once this is fixed quantity, what do we have here? Then if we have this fixed quantity, then this relation for sigma square will just be a function of W1 square, W2 square, W1, W2, and so on. So it's a function of just W1 and W2. So your problem is to minimize this. Minimize this with respect to what? Minimize this with respect to W1 and W2. That means determine W1 and W2 so that sigma square is minimum. Why minimum? Because I want the risk to be minimum. So if I assume that there are certain conditions, I'll not go into the details of this. Suppose that your sigma 1 is less than or equal to sigma 2. See, sigma 1 and sigma 2 are both going to be positive because this is a standard deviation. Standard deviation by definition is positive. And of course, they cannot be zero because if a standard deviation is zero, that means there is no risk. So it is not a stock, it's like a bond, which is not what we are considering. Assuming further that if rho 1 2 equal to 1, then sigma 1 not equal to sigma 2. So on top of it, see here we assume that sigma 1 less than or equal to sigma 2, but the equality will not hold if assume that if rho 1 2 equal to 1, then sigma 1 is not equal to sigma 2. So those are the cases that will be dealt with separately. Now, suppose that the combination of W1 and W2, the W1 and W2 values for which sigma square will be minimum, I denote this with W1 comma mean and W2 comma mean. And you can show that these two values which minimizes sigma square is given by sigma 1 into sigma 1 minus rho 1 to sigma 2 divided by this denominator. And naturally your W1 mean is going to be 1 minus W2 mean. You just take 1 minus of this because W1 plus W2 is going to be always equal to 1. Now, once you put this value of W1 mean and W2 mean in this relation, if we substitute the value of W1 and W2 here, then we will get the corresponding return as well as the variance. We substitute this value of W1, W2. So, and for those choices of W1 and W2, what is going to be the expected return is given by this, and what is going to be the variance will be given by this. And remember, this variance that you have, well, those W1, W2 is a result of minimizing the variance. So once you substitute it back to the value of sigma square, then the sigma square that you get is the minimum variance portfolio, or what is called as the MVP. Now, how do I derive this? Okay, how did I arrive at these two values of W2 and W1? Remember, I arrived at this by minimizing the sigma square. How do I minimize the sigma square? It's a function of two variables, but the advantage is that since W1 plus W2 is equal to 1, so that means I can convert this into a function of a single variable and then use my usual differential calculus or the differentiability test in order to optimize or minimize the variance. So accordingly, I suppose I write W2 is equal to S, so then W1 is going to be 1 minus S because the sum of them has to be equal to 1. So then what is going to be mu? Mu is going to be W1 as mu1, which is 1 minus S mu1, plus W2 mu2, that is plus S of mu2, which can be written in this particular form. What is going to be the variance? So the variance is going to be a W1 square, which is 1 minus S square sigma 1 square, plus W2 square, which is S square sigma 2 square, plus twice W1, which is twice 1 minus S into W2 into S into rho 1 to sigma 1 sigma 2. And this can now remember that this contains quadratic terms, that is S squared terms. It contains linear terms, that is just the S terms and some constants. So I write this as in the quadratic form as this expression into S square minus this expression into S plus sigma square. So now you see, now this minimum variance can be found out by finding the minimum of this function of a single variable S. And this we can accomplish by taking the derivative test. So I take the derivative of this. So what is this going to be? This is going to be this quantity into twice S minus this quantity without the S plus 0. So this gives us this quantity, and then I solve for S, and that is going to be the S minimum. That is sigma 1 into sigma 1 minus rho 1 2. And what does S mean? S was my W2. So this S mean is the same as W2 mean. See, this is the W2 mean, which is the same as S mean. And once you have this S mean, you have 1 minus S mean, then you substitute this value. This is going to be W2 mean, W1 mean. You substitute the value of this S mean here. So for example, or instead directly you can put your S mean value here and here to find out the corresponding sigma mean square, which turns out to be equal to this quantity. So I leave this as an exercise to you, first exercise. And second thing is that if you take the second derivative test here, that means what will you have? You need to prove for the minimum, you need to prove that derivative is second derivative is positive. So here you can take the second derivative. The second derivative is going to be this term. And by making use of the assumptions that have been given here, these assumptions, you can prove that the second derivative is positive, thereby ensuring your minimum, ensuring that the value of S mean that you have obtained here does indeed minimize your sigma square. Okay, now I want to
हाँ, हमने वो तो भूत था। हम नहीं थे, हम तो यहाँ बैठे थे।
Yeah, there is some issue I think from sir's side. So please wait for a minute. Am I audible? Dr. Pranadas, Drumit, am I audible? Yes, okay. Maybe there is some issue with sir.
Yes,
He'll be
you
joining again, right? He has disconnected, so he'll be joining again. Just wait for a minute, couple of minutes. Yeah, thank you, sir. Thank you for your nice comments, and hope we will have, these kind of sessions. All the sessions will be this kind of thing. So let me connect with sir whether he is able to join or not. I think sir is having some issue, so please wait for a couple of minutes. He'll be joining soon, right? So we have to wait for a couple of minutes, maybe 2-3 minutes. Yeah, or we can say you can take a break of 2-3 minutes, maybe, right? So we are here only. He is saying that he'll be joining soon, right?
Kuldeep sir, may I have a question? Hello.
Actually, we are on a break for 5 to 10 minutes, sir. Everybody went on break as you were disconnected for a while.
No, don't think like that. Sir will be joining soon. Sir is on the call only. Just a minute.
Okay.
Yeah, I request all the participants, you can take a 5-minute break. Actually, sir is having some issue with his PC. So he'll be joining very soon, within 5 minutes. So let's now have a break of 5 minutes. Is that fine? Dromit, Pranav sir, Vana Kumar,
Yes,
right?
sir.
So we are going to have a 5-minute break, sir. Yeah, thank you everyone, right? So we'll be joining soon at 4:05. Thank you.
So now I just want to make a quick few observations. One is that a few more observations based on whatever you have done, and I will explain this one by one, and then I'll just sum up whatever has been decided, whatever has been discussed. So suppose if your rho is equal to 1 and sigma 1 equal to sigma 2, then all weights have the same and therefore the minimum risk. So it does not matter what weights W1 and W2 you are choosing. If your rho is equal to 1 and sigma 1 equal to sigma 2, then you can, any choice of any combination of weight will give you the same risk, which will be equal to. So you can actually invest in only one asset. You can invest in the second asset. You can take any the same as the minimum risk level. Now, if your rho is strictly less than sigma 1 by sigma 2, but greater than or equal to -1, then your S mean will lie strictly between 0 and 1. So obviously 1 minus S mean will lie strictly between 0 and 1. So that means your weights are short selling. If your rho is equal to sigma 1 by sigma 2, except the case already considered here where rho equal to 1 and sigma 1 equal to sigma 2, then you can show that S mean is 0. So that means the minimum variance is achieved by zero investment in the second asset. So that means minimum variance is achieved by investment only in the first asset. Then if your rho is greater than sigma 1 by sigma 2 but less than or equal to 1, this is equivalent to S mean being less than 0. So that means that you have to have a negative weight. So in order to achieve minimum risk, you need to have resort to a short position or short selling. So if you observe carefully, what I have done here is I have considered that my rho is greater than or equal to -1. Consider that the rho is lying between -1 included but strictly less than sigma 1 by sigma 2, then no short selling is required for minimum variance. If your rho is strictly greater than sigma 1 by sigma 2 but less than or equal to 1, in that case you will need short selling in order to get minimum variance. And the third case where rho is equal to sigma 1 by sigma 2, in this case two things can happen. Variance by investing only in the first asset, and if your rho equal to sigma 1 by sigma 2 with the specific case that rho equal to 1 and sigma 1 equal to sigma 2, then it does not matter what weights you are assigning. In all cases, you will end up getting the same risk, which will be the minimum risk. So these four things you can actually work out as an exercise from this formulation, from the formulation that you have here. It's a little bit of algebra, but you can work this out on your own. Okay, so now I have this setup that, okay, what should be my choice of W1 and W2 in case of a two asset portfolio with the objective of minimizing the risk given by the variance. In case of a multi-asset portfolio. So that means that where we move on to a portfolio with arbitrary number remember the weight is what? Weight is the number of units of the ith asset multiplied by the value of the asset, that is your total investment in the ith asset, divided by the total investment in all the assets. So this V0 is nothing but summation of theta I0 VI0. Now, when you are talking about more than two number of assets, it is practically more useful to introduce a few matrices and vectors that we will need in the due course, and then we will also identify the reason for their introduction. Okay, so first of all, let us have this weights. So remember that we are now considering n number of assets. So those weights are going to be W1, W2 all the way to Wn. So this we will write in a vector form as a row vector and call this the weight vector or weight matrix W. Then we take a vector of or a matrix of ones or a vector of one where all entries are one with the number of such ones being little n. And then we take this to be, we define this vector to be O. So then what is the first condition in terms of weights? So the weight is given by summation. The condition on weights is summation W by I is equal to 1 to n. And this can be written as O W transpose equal to 1. Remember, this O is a 1 by n matrix. W transpose is a n by 1 matrix. So O W transpose is just a number. So it will be given by 1 into W1 plus 1 to W2 and so on. So this left hand side is nothing but summation of W by I is equal to 1 to n. So any portfolio that satisfies this property is called an attainable portfolio. So this means that any portfolio or combination of W1 to Wn such that summation of Wi equal to 1 or equivalently this condition holds, it is what is known as an attainable portfolio. Okay, now when you are talking about multi-asset portfolio, we have to obviously talk about returns and risk. So accordingly, you recall that we had used the notation mu I to be the expected return for the ith asset. So what do we have? Since we have n number of assets, so we have the corresponding expected returns to be mu1, mu2 all the way to mu1. And we denote this by M. So this is basically the matrix. This is the matrix or the vector of the expected returns. So remember that for the portfolio, the expected return is summation mu I Wi. And this can be written as MW transpose equal to V. Remember, M is this 1 by n matrix, and W transpose is the transpose of this, which is a n by 1 matrix. MW transpose is going to be nothing but this summation, and this is equal to mu. The third matrix that you choose will denote a matrix C whose entries are given by Cij, and Cij is the covariance of Ri Rj. So then this risk, double summation Cij Wi Wj, remember that this was the variance of a portfolio of n assets. You can show that in the compact form, this can be written as WCW transpose becomes a single entity, namely sigma square. Okay. So that this expected return of the portfolio can be written in terms of this matrix. And we now have a matrix of covariance so that the variance of the portfolio can be given in terms of this covariance matrix C. Now this brings an efficient frontier. From a mathematical point of view, this is the relationship between these weights W1 to Wn of a portfolio to the corresponding points mu, sigma, mu for a portfolio. So what do I mean by this? See, you take one combination of, see, your mu i's are all fixed. So this mu m vector is fixed. Remember, once you have chosen the n assets, this m is fixed, does not change. Your C is fixed. The only thing that you can vary is your Wi. So now for different values of Wi, since the mu i's are fixed, for different combinations of W1 to Wn, you will get one corresponding value of mu and one value of sigma square. So we take one set of mu. So like this, you know, there can be infinitely many combinations of W1 through Wn, which adds up to 1. I can take it infinitely many ways. And for each of those ways, there is going to be one pair sigma mu. Now, since there are infinitely many combinations of W1 through Wn, there is going to be correspondingly infinite as I mentioned, that one combination of W1 through W2 will give one pair sigma mu. Another combination will give another. What we are doing is, we will remember that I had said that sometimes we will use sigma square as a measure of risk, and sometimes we will look at this standard deviation sigma as the measure of risk. And now we consider the curve with the point sigma mu. So remember that we had infinitely many combinations of W1 to Wn, and using the formula, we can find infinitely many points sigma mu. Suppose you take the sigma along the x-axis and mu along the y-axis. So this will be in a two-dimensional coordinate system. There will be infinitely many such values. And amongst those values, there is going to be one combination W1 through Wn for which the sigma is going to be minimum, and that corresponding, suppose that it is W1 mean, W2 mean, all the way to Wn mean, is the one which gives the minimum value of sigma, or equivalently sigma square. So when I put W1 mean, W2 mean all the way in the formula, the corresponding sigma and mu that I get, I will denote that by sigma mean comma mu mean. So the set of points sigma mean comma mu that gives minimum risk for each expected return is called the Markovians efficient frontier. So this means that for a fixed, so basically this means that it is for each expected level of return. So this means that if I fix my return, now for that return there could be many different values of sigma. Amongst them, whichever is the smallest value is the one which will be and then the curve that is generated out of it, it is what is known as the Markovians efficient frontier. Now, please don't get intimidated by what I'm saying here. I'm going to explain this graphically. So you see, suppose I consider a 3-asset portfolio. So instead of, I take my little n to be equal to 3 here. So suppose I have 3 assets with the weights W1, W2, and W3. Now I consider this combination of weights W1, W2, W3. All right. Now, what is going to be the surface where W1 plus W2 plus W3 equal to 1? It is going to be this surface. So what is going to happen is that any combination of W1, W2, and W3 is going to be from this surface, and for each combination of W1, W2, W3, I will have a corresponding sigma mu. So suppose I take this W1, W2, W3, sum of which is 1, and I calculate mu sigma, and that is this mu sigma. I take another W1, W2, W3, and then I'll calculate another mu sigma here, which I have not shown here. So I can calculate infinitely many such 3-dimensional coordinates W1, W2, W3, and for each of them I will have a mu sigma. So that will generate this curve and points to the right hand side. So you can prove that it is going to be a curve like this. Now, since this curve looks like a bullet, so this curve, which includes all this curve and everything to the right hand side, this is the complete list of, or complete combinations of mu sigma corresponding to the complete collection of W1, W2, W3, and this looks like a bullet which is why this is called a Markovits bullet, and it's called a Markovits bullet because Markovits is the one who derived this. Now, remember that what I said here, I said that it's a set of points sigma, mean, comma, mu. So observe here, suppose that I fix my mu here. Now, at that level of mu, I can draw a straight line here, and if I so at that level of mu, I can get infinitely many combinations of sigma and mu, but amongst those sigma and mu, the one with the minimum sigma is the one which lies on the curve. Suppose that I take another mu value here, then I draw a line here. From this point onwards, there are infinitely many values of sigma comma mu, but the this means that these points on these lines are nothing but the fixed mu, which results in the minimum corresponding sigma. Now, instead of fixing mu, if I fix sigma, so suppose I fix my sigma and I draw a vertical line here, then you will see that along this line, the sigma is same, but the expected return is going to be highest here. So obviously, as an investor, I only want either the scenario where my expected return is fixed. If I fix my expected return, I will take the portfolio with the lowest risk, or if my risk is fixed, I'll obviously going to take the portfolio with the highest return, or I'm going to simply take that portfolio which is the minimum risk. And remember, these were the three objectives that I had said right at the beginning. Fix your expected return and minimize the risk. Fix your risk and maximize the return, or you simply look at what is going to be the minimum risk. So these values which satisfies these three conditions are just those values starting from this tip here along this curve at the top. And that is why this is known as the efficient frontier, because these are the best portfolios for a that best in the sense that for a given level of return they give minimum risk, or for a given level of risk they give the maximum return, or they simply give the minimum risk. And this mapping here is basically is a one-to-one onto mapping. You can show that this is a one-to-one onto mapping. So that means every point on this curve here would have come from a unique value of W1, W2, W3. And the same argument can be extended in case of the right-hand side does not change, only the left. You can extend it to an n-dimensional system where there are n number of facets, but the right-hand side does not change. So the first thing is basically everything that is feasible. This is all the possible portfolios will be on the curve and to the right, but the portfolios that you are interested in are only those ones which end up giving you mu sigma starting from this point and lying only on those curves. And as an investor, you should be picking up portfolios only from these particular curves. Okay, now this is fine. I mean, graphically, of course, I can't figure out what is my W1, W2. This is very good if you want to intuitively see what is going on. But in precise terms, you have to actually figure out the numbers W1, W2, W3, which will give you points on the efficient frontier. So accordingly, we'll first talk. Now we are going to give the most general framework, and we'll talk about the minimum variance portfolio. So what you are going to do now is we are going to do the same exercise that we had done in case of a two-asset portfolio to find the portfolio with the smallest variance or smallest risk amongst all combinations. And the smallest variance is given by, you can prove that, and this is stated as a theorem, that the weight W, which is W1 through W1, will be given by OC inverse divided by OC inverse O transpose, where O, you remember, was a vector of length n of all ones, and your C was a covariance matrix that I had defined. Now, how do you prove this? Now, remember that your sigma square was WC W transpose. So since this is only a minimum variance portfolio, so my goal is to minimize sigma square which in the vector form is WCW transpose, subject to what constraint? So right now the only constraint is the sum of the weights is going to be equal to 1, which in the vector form was OW transpose equal to 1. So the problem is minimize WCW transpose, which is the variance, subject to the constraint OW transpose equal to 1, which is the sum of the weights equal to 1. Now, this is a multivariable, is an optimization problem in multivariable. So it's a function of W1 through Wn. So obviously you 1 minus s, you get a function of single variable. Use your high school differential calculus and do. So for this kind of problem, we have to use multivariable calculus, and we use the method of Lagrange multiply. So accordingly, we define the Lagrangian. The Lagrangian is given by this the function that is to be minimized, that is WCW transpose minus a Lagrange multiplier multiplied by this constraint in the form of LHS equal to verify for yourself, and you take this derivative with respect to W1, W2 all the way to Wn. So you will get n number of equations bring them together in the vector form. So you get twice WC minus lambda 0. So you have got the weights. So it's very nice. You have got the weights of the portfolio which gives the minimum risk. So you got weights equal to lambda over 2 into OC inverse. Now you know what is O. O is the vector of all ones. C inverse is the inverse of the covariance by 2. So in order to determine that, what you do? You take this W here and substitute in the constraint. So once you substitute this W in the constraint, so then what does it become? It is OW transpose. So it is nothing but O into OC inverse into lambda by 2, this quantity transpose equal to 1. And then you can solve this for lambda by 2 is as, and then you substitute this value of lambda by 2 here to get the weight now in terms of known quantities. Until this step, lambda was still unknown, but now you have everything in terms of known quantities. And at this point, all you need is just matrix multiplication. Note that the denominator here actually is a scalar. So obviously, there is no matrix division that is involved. So this is the weight that you have got. So remember that once you have chosen your assets, you can calculate what is your C. And once you have that, you can put it in this formula and then say whatever is the vector of n you get, that is going to be your minimum variance portfolio. And then you can use that to calculate the number of units of each of the assets that you need to purchase in order to make this investment resulting in a minimum variance portfolio. Now, at this point, I want to digress. Remember that this efficient frontier was what? The efficient frontier is either the minimum variance, which is what I have found just now, or it is the constraint case where you fix your mu and find the minimum variance, or you fix your sigma and find the maximum return. So this was the first goal that we have basically found out. So what we have found out now is that this point here, the values of W that we have just now found in terms of O and C inverse is those values of W1 through Wn, which will give you this point here. And the next thing that we want to find out is to basically so accordingly, we need to find the portfolio with the smallest variance among all portfolios in the ascendable set. So here, if you do, you can either find the weights which gives this line either by fixing your mu and minimizing sigma, or fixing sigma and maximizing mu. Both of them, either of them, you don't need to do both. Either of them is going to give you this entire this entire curve here, or rather the weights which gives this entire Markowitz efficient front return to be some mu. It is given by this a slightly more complicated expression than the previous one. And remember here, now you are fixing your mu. So anyway, the other terms here, M, C, O, everything else is known. And the new term, that mu that has come in, that is fixed, because now you are looking at the top part of the efficient frontier, where you are fixing your mu and then finding out whatever is the minimum risk. So mu is also in this, for this problem, mu is now fixed. And interestingly, you can also, if you observe that here, if you expand this, you will see that each of the weights W is actually a linear function of mu. But that's another story which, which I don't want to go through now. So again, how do you prove this? Same problem, sigma square is equal to minimize this variance subject to sum of the weights being equal to 1 in the matrix form as OW transpose equal to 1. But remember here we have now an additional constraint that MW transpose equal to mu. That is, you have fixed your weight of the portfolio to be some quantity mu. So then again we define the Lagrangian, that we take G to be WCW transpose minus this constraint OW transpose minus 1 into lambda 1, and on top of it now we have to put a second constraint MW transpose minus mu into lambda 2. So it is the same approach as the previous one, except that you have instead of one Lagrangian Lagrange multiplier lambda, you have two Lagrange multipliers lambda 1 lambda 2, because now you have two constraints instead of one. So again, we take the partial derivative of this with respect to W1 through Wn, and we end up getting W is equal to lambda 1 over 2 OC inverse plus lambda 2 over 2 MC inverse. So now you have got the weights which will result in your mu sigma on the efficient frontier. Now here your O, M, and C inverse are known, but you again now have two unknowns, lambda 1 and lambda 2, and you have to determine them. W transpose equal to mu and OW transpose equal to 1. So this is what you get. Now what you get here, you see, you now get a system of two linear equations where this component MC inverse O transpose, MC inverse M transpose, OC inverse O transpose, and OC inverse M transpose, and mu and 1 on the right hand side, these are known. So that means this is a system of two linear equations in lambda 1 and lambda 2, or you can view it as lambda 1 by 2 and lambda 2 by 2. So this again is a high school problem. You then solve for lambda 1 by 2 and lambda 2 by 2 using Cramer's rule or just by hand, by elimination. And
Hello.
1 and lambda
Hello,
2. Yes.
Sir, is there any possibility that coefficient matrix is singular matrix? If it is singular,
Yes,
then we
yes,
cannot find.
yes. The coefficient matrix in a rare case it may end up being singular. So for that you have to check, but it is positive symmetric. So in case it's singular, then you have to have some other ways of dealing with it. So in the assumption is that here I'm assuming that C inverse exists. All right.
Okay.
So that's a very good question. But typically C inverse will exist. So some of the properties of C inverse, it is, I think, positive definite. It is obviously it is symmetric, and there are certain other properties of C inverse. So you'll have to look up those properties, but typically it is going to work. So anyway, I mean that is implicitly understood that if a formula inverse C inverse, that you are assuming that C inverse is going to exist. So here you have lambda 1 by, once you solve for lambda 1, lambda 2 here, and you substitute these values here, which I have not done, you immediately get this form. See this determinant and all, these are obviously something that have followed from the Cramer's rule. Okay, so this concludes our discussion for the time being on the Markowitz efficient frontier. The next thing that I want to talk about is the capital asset pricing model. All right. What do you do is that, So in case of capital asset pricing model, there are two main problems which dominate this discipline. What is the best course of action in investment situation, which is what you have already done, and then the determination of the correct arbitrage fair or equilibrium price, something which you must have done with Professor Karandikar. So what we will do is that we'll now mainly focus on the capital price asset pricing model. This was developed in 1960s through mainly due to Sharp, Linter, and Mossin. And it's the reason why it appears in our narrative here is because it follows logically from the mean variance portfolio theory. What we talk about, we now talk about market, we'll talk about the One Fund Theorem, and then we'll move on to capital. So let us talk about market equilibrium. See, in this context of the discussion, when I talk about market equilibrium, I mean the following. In this setup, I assume that everyone is a mean variance optimizer and everyone agrees to the probabilistic structure of assets. So everyone agrees that the returns can be a random variable. They believe this Markovians theory of mean variance optimization. They believe in the efficient frontier theory, and they assume that there exists a unique race-free rate of borrowing. So the assumption is that there is a single interest rate which is used for borrowing and lending, and then there are no transaction costs. It's a simple case, but of course, subsequently more modifications of this have been incorporated. Now, when you go to borrow and lend, you obviously know that when the bank issues you a fixed deposit, the bank is taking money from you, so they're effectively borrowing. So the rate of interest that they are going to offer you is going to be less than the rate of interest they will charge you if you go to them for a loan. Now, that is what happens realistically, but here for the simplification purpose, you assume that both these rates are identical and there is no transaction cost, right? So that there is no fees or anything like that. Just to have the basic setup and to have an intuitive understanding of what is going on. But as I said, there are results where the extension of this, which relaxes this condition and makes it more realistic. For that, you have to look up in the literature. But for the context of our discussion, we'll just focus on this assumption. Now, this brings us to a classical theorem called the One Fund Theorem. And the One Fund Theorem says that there is a single fund F of risky assets such that an efficient portfolio can be constructed as a combination of this fund F and a risk-free asset. And this magic fund is known as the market portfolio. Okay, now I have pumped in a lot of information here is that now there is a change that has come from the Markovians setup to this capital asset pricing model setup. And the factor that turns Markovians model into the CAPM model is the now I am making it more, looking at an extension of this, where the assumption is that in addition to n number of risky assets, I can also invest at a risk-free asset, an example of which is bond. Now, with that, once we are in this framework where there are n number of risky assets or stocks, for example, plus one risk-free asset, then we can have this One Fund Theorem. So now once we have this n plus this one number of asset, obviously for this also we can have an efficient in this case, the efficient frontier, any portfolio on the efficient front fund, which is known as the market portfolio. So that means once you have the risk-free asset and you have determined what is the market portfolio, then you can draw the entire efficient frontier, which may not be a curve, the entire efficient frontier by making use of information or taking a combination of these two. by combination, I mean that the efficient frontier could be as a result of putting 50% money in risk-free asset and 50% money in this magic fund, 25, 75, 75, 25, 40, 60. So all possible combinations. So now what do we do? So now I want to give, so I have put in this information, but now at the next step that we have to do here is we have to now extend this so that we first of all get a mathematical framework, and secondly we get the graph, the Markovians bullet. How is the Markovians bullet now going to look like, and how is the consequent efficient frontier look like? What is going to be the picture once we bring this risk-free asset into consideration for our portfolio? So then what do you do? So again, we considered A1, A2, AN, n number of assets with weight W1, W2 all the way to WN. But on top of it, we consider a risk-free asset ARF whose weight I denote as WRF. So now we don't have only n weights, but we have n plus 1 weights. So this means that WRF, that is the weight of the risk-free asset plus the weight of all the risky assets, this must be equal to 1. So in the Markovians framework, only summation WI is equal to 1, but in the Kaplan framework, we have summation WI plus WRF is going to be equal to 1. And then I define W risky to be equal to summation of WI, that is the sum of the weights of the risky asset. So that means the fraction of money that you have put in risky asset. What is W risky? Summation of WI is 1 minus WRF. So I now have two weights, WRF plus W risky equal to 1, and naturally this W risky is going to be equal to be less than or equal to 1, assuming that your WRF is not going to be negative. So then I again calculate the expected return as before. So the expected return will be summation WI mu I plus WRF mu RF. What is this? This is nothing but WRF mu RF plus what I call as mu risky. So I'm just calling this as mu risky. So that is the expected return that you get from your risky investment, and this is the one that you get from your risk-free investment. And then what is this should be variance of return. So the variance of return is going to be sigma square is variance of WRF plus this. So variance of a constant plus a random variable, what is this going to be? This is going to be variance of a constant A plus X is the same as variance of X. So this is going to be variance of A plus X is variance of X, which is summation WRI, and this I will call sigma square risk. So that means sigma of this portfolio is the same as, so the risk of the portfolio including the risk-free asset is the same as the risk of a portfolio without the risk-free asset, or just the risk that comes from the risky components of the portfolio. Okay, now it is now time for us to actually collate and connect these two things together. So accordingly, what you do is that we consider a portfolio without a risk-free asset, and then we make a connection with this portfolio with the risk-free asset. So the portfolio formed by removing the risk-free asset and beefing up the weights of the risky assets. Now we make the connection between the original portfolio and the newly derived portfolio. So what I'm doing here is I'm doing the two things. First of all, see, I have already, when I have started this discussion on Kaplan, what I have done is that I have assumed I have already included the risk-free asset. Now suppose that my 20% of my money was put in the risk-free asset and 80% was put in the risky asset. Once I have done that, now suppose I remove the risk-free asset and I increase the weights of the risky assets so that they add up to 1. So that means what I'm going to do, whatever weights I had for the risky asset, each of them, I will multiply this by 1.25. So what is going to happen? When I multiply this by 1.25, that means then it becomes a legitimate portfolio. All right. See, because once I remove the risk-free asset, I cannot have a portfolio with the risk, those the sum of the weights of the risky assets being equal to 0.8. So I make a proportional increase for all their weights in order to get the sum of the weights being equal to 1. So in this case, what do we have? Now we consider the previous portfolio, which had the risk-free asset, as the original portfolio, and this new portfolio that I have created without the risk-free asset, and then followed by jacking up the weights, I call it the derived portfolio. So what is mu? Mu is equal to WRF mu RF plus summation WY mu Y. We have already seen that. Now what I can do is I can take this plus W risky into summation WI by, so I can multiply and divide the second term by W risky. Now remember, once I take this W divide by W risky, that means what? So if my W risky was 0.8, so 1 over W risky is 1 over 0.8, which is 1 over 4 by 5, which is 5 by 4 into WI. So what I can do is this, if I take WI over W risky, this is nothing, the sum of this will become a new weight, say WI prime, and the sum of those WI primes is going to be equal to 1. So forget this part, just look at this way. This is basically the weights of this derived portfolio after removing the risk-free asset and followed by jacking up the risky weights. And so consequently, what is this going to be? This I can now consider. Now what is this going to be? This is now going to be the summation of weights into mu I in the original Markovians framework, which comprised of only the risky assets. So this can be written as WRF mu RF plus W risky into, this is the mu of the portfolio which is derived. So this I write it as mu dir. In a similar manner, I can take this variance of the portfolio. Remember this mu and this mu sigma, these are the mu and sigma for the portfolio which includes the risk-free asset. And this mu dir is the portfolio which includes only the risky assets resulting from jacking up the weights. So I can do the same exercise here by multiplying and dividing by W risky. So I divide by W risky, multiplied by W risky, and take it outside. So I get W risky square into variance of this summation. So this becomes W risky into sigma squared dir. So that means I get a relation connecting the mu sigma of the portfolio with the risk-free asset with the corresponding mu and sigma of the derived portfolio, which only comprises of the risky assets. So this mu sigma, you view this as kappa mu sigma, and this mu dir sigma dir, you view this as Markovians mu sigma. Now remember that WRF plus W risky equal to 1. So if you use this, so from here you can write WRF. You can write WRF is equal to 1 minus W risk. So that means on the right hand side there is going to be no WRF because mu RF is a fixed quantity. So there will be no weight. The weight RF will be gone, and likewise the same thing here. So substituting this,
I think so. You are not audible. Is it? Yeah. Now it's fine. Sir, I think you're not audible. Can you hear us?
Hello, Kuldeep.
You're audible.
Okay, I'm audible. Okay, fine.
Yeah, now you're audible.
Yes. Okay, I will start off from the point where you got disconnected. I noticed when there was a network issue, so I'm going to start off from the same place.
Yeah, sir. This is the slide.
Okay.
We can see the slides.
Yes, yes, I know this is the slide. Yes, so you can actually eliminate W risky now, and then what you get? You get mu is equal to mu dir minus mu RF over sigma dir into sigma plus mu RF. So now you have got a relation which connects mu and sigma, and graphically it looks like this. So now I want to make a very important point here. See here, this mu dir and sigma dir, there are many combinations of mu dir and sigma dir, right? See, mu dir and sigma dir basically get a combination of sigma and mu, a corresponding combination of sigma and mu. So that means this mu sigma and mu dir sigma dir, they can be connected by a real line. See, remember that mu minus mu RF over sigma is mu dir minus mu RF over sigma dir. So that means both of them have the same slope. So if you consider a pair mu dir and sigma dir, remember that mu dir and sigma dir was derived from mu and sigma. So every pair mu dir and sigma dir and mu sigma, they are linked to each other and they have the same slope. So that means that this mu sigma and mu dir and sigma dir, this is going to be a straight line. Now this is one mu sigma and the corresponding sigma dir mu dir. There is going to be another one, and remember that if your sigma is equal to 0, then mu will be equal to mu RF. So when your sigma is equal to 0, your mu is going to be equal to mu RF. So you should view this as a linear relation. So remember that you should view this as a linear relation in the sigma mu plane, and you can treat mu dir and sigma dir as fixed quantities because they are derived once your sigma and mu are known. So what you have is that you get many such lines like this, and you end up getting the line, the last line or the line with the highest slope is the one which will be here. So in order to sum this up, what does this mean? See, this means, see, this is going to be, this curve that you have is basically the original Markovians bullet, and this is going to be the original Markovians efficient frontier. And remember that this point which lies here, this is a part of the Markovians bullet which involves only risk-free assets. But once you involve the risk-free asset, then the efficient frontier becomes this line. It no longer remains the curve, but it becomes this line, which has the largest slope amongst all the straight lines given by this equation. And the point of tangency, that is the point at which this line, that is this line with the maximum slope, the point at which it is tangent to the Markovians efficient frontier, that point of tangency obviously comes from some weights, and which means that it obviously comes from a particular portfolio, and that portfolio is known as the capital market portfolio or the market portfolio. The reason this is called the market portfolio is that after an extensive work, and if you are interested, you can look up the book of Francis and Kim, you can show that the investment in this particular portfolio, or the weights which result, the weights which gives you this particular point is going to be the same as the weights resulting from the market capitalization of all the assets that are there in the market. So what you do is basically, what is the investment in a market portfolio mean? The investment in a market portfolio means that you basically have bought all the shares that are available in the market. So then and then you divide this by sum of your investment in the overall market. So whatever weight you get there, that weight will turn out point of tangency is what is known as the capital market portfolio. So in summary, the efficient frontier in the Markovians framework is this curve, is a bullet-like thing, the top part of a bullet. The efficient frontier of, if you include a risk-free asset or the CAPM framework, is a straight line. Thirdly, the point at which these two meet or are tangent is a capital market portfolio because its weight mimic an actual market. And fourthly, as I said, the One Fund Theorem is that, if you remember, the One Fund Theorem said that basically, now when you are looking at the Markovians framework, you want to invest in the efficient frontier. Likewise, when you are in the CAPM framework, you want to invest in the efficient frontier, which is given by this straight line. And then any point on this straight line, any value of any point on this straight line can be obtained as a linear combination of mu RF plus a linear combination of this and this. So this means that on this efficient frontier, if you want a portfolio on this efficient frontier in the CAPM framework, then you take a combination of the risk-free asset and the magic fund or the market fund. So this graph here, the fact that this entire line can be generated as a linear combination of this and these 2 points is the one that manifests as the One Fund Theorem. It says that there is a single fund F of risky asset such that any efficient portfolio can be constructed as a combination of this fund F and the risk-free asset. So remember that this fund, since this point also lies on the efficient frontier of the Markovians bullet, so that means that it comprises of only risky asset. So this fund F comprises of only risky asset plus, see, it can be constructed as a combination, says that there is a single fund F of risky asset, which is this our market portfolio, so that any efficient portfolio in the CAPM framework, which involves, where you must involve a risk-free asset, this can be constructed as a combination of this fund F and a risk-free asset. So that means that you can write this as a combination of a risky portfolio plus a risk-free asset or any combination of. So as an investor, it is enough, instead of looking for what to invest where, it is just enough. Suppose you decide that you want this level of mu, then you can just put here and choose the appropriate value of mu RF and this, which will give you a value here. So you don't need to invest in a lot of things. All you need to do is you can invest in the capital market portfolio and you can invest here. Now, capital market portfolio, how are you going to invest? Obviously, you something and you will get a reasonable mimicking of the capital market. So the punchline in the CAPM framework is go and get some SBI fixed deposit and put some money in some NSE 50 or some Nifty 50 index in whatever proportion you want, depending on where on this line do you want to find yourself in. Okay. So I want to do one more slide and then I will conclude. I'm running out of time. So if you observe here that this point sigma is equal to 0. So this coordinate of this point is 0 mu RF, and the coordinate of the you can show that it's a derived portfolio because it lies on this time and it comprises of risky assets. Okay, and this particular tangent line is what is known as the capital market line, and the point of tangency is known as the capital. Talk about this capital market line, and I will actually determine what is going to be the weights of this portfolio. What is the weight, approximate weight you can get? Market portfolio. So this derivation is something I will do, and I will talk a little bit about systematic and unsystematic risk, and talk a little bit about this concept of beta. And then I will do CAPM as a pricing formula before moving on to my discussion on MATLAB. Okay, so I am done with.
Yeah, thank you so much, sir. Any questions from the participants? Though they have already said in the chat box. So
Hello?
Yes,
Yes.
sir. Yeah. So any questions from the participants? Very quick questions we can ask. Otherwise, sir will be with us tomorrow also. So you can ask then if you get any question in your mind.
Hello,
So,
Siddharth sir.
yeah.
Sir, I want to know about what is risk preference parameter. So when you model a mean variance portfolio, which means trade-off between risk and return. So if I'm using a risk preference parameter, in that case, what is the if
I completely Sahuji, you are speaking? Sahuji is speaking?
Yes, sir. Hello.
Yes.
Sir, am I audible? Hello.
Yeah, Sahuji is speaking, sir.
Sir, am I audible?
Can you yes, you are audible now. Can you
please
please
to me, but I think sir is not able to listen.
Yes, sir. Sir, I want to know about what is risk preference parameter. If I model a mean variance portfolio, that means I'm writing that a trade-off between risk and return by the help of a risk parameter. So in that case, if I'm getting some objective value, what does that mean? So I am getting the weight of vector, but what is the objective value means?
Yes. So the weight of the once you have the weight of the vector, so what you can do is that one to stock 3.
Sorry, sir, it's not audible to me.
Sir, actually, you can turn off your video, then maybe it will be. Yeah.
Okay, fine. So in a very simple terms, what is the
hello.
Yeah,
and
sometimes
you do this optimization. You look at the historical data and you calculate your mu1, mu2, mu3, and everything, and you do the calculation. Then you find out that your weight W1 is 0.5, where W2 is 0.3, where W3 is 0.2. That means it is telling you that you put
sir, actually, I am not audible. Your voice is not coming to me.
yes, sir.
So if possible if possible, then tomorrow we'll discuss that question.
Okay, fine. But Kuldeep, let me finish. Let me finish. I'll finish it quickly. I'll finish this quickly. So this means that out of 10,000, you invest 5,000 rupees in the first company, 3,000 in the second company, and 2,000 in the third company.
Yes,
that is the meaning of this. It will help you decide your investment strategy. Okay, Kuldeep. Yes, it seems that you are in a hurry. So I know you had a long day.
No, sir. Actually, your voice is not audible to me. So that's why I'm saying if today is not possible, then we'll discuss tomorrow in the first section.
No problem. Sir has explained it again and nicely. So thank you so much, sir. And
Thank you,
All
Kuldeep.
the participants will be having one more session. Yeah, sir, we'll be having one more session by sir tomorrow. So please do join us, and let me again thank you, sir. It's such a nice, such a beautiful session on portfolio management. I mean, hardly we get these kind of things in. Yeah, someone has commented that it is an excellent session. So hardly we get these things written in a book. So literally, sir, we got benefited from this. So thank you once again, sir, and we'll be very happy to have you tomorrow again. So I'm winding up this session now. Thank you,
Yes,
everyone.
please
Thank
do.
you again.
Yes, please do. Tomorrow we'll have MATLAB.
Yeah. So as you said that you'll be doing some hands-on on MATLAB.
Yeah, then I'll just make use of some inbuilt tools of MATLAB, just demonstrating people how they can use the toolbox. All right.
Yes.
Okay, Kuldeep, and also tomorrow I'll try to join a little early to test because I don't know.
Okay, sir. I'll join little. I mean, we can test it. No problem, sir.
খুব ভালো হয়েছে স্যার।
Kuldeep, we'll discuss this WebEx issue on phone. I'll discuss with you because it is continuously
Sure, sir.
খুব ভালো হয়েছে সিদ্ধার্থ স্যার, অনেক কিছু বুঝতে পেরেছি, ধন্যবাদ।
Thank you everyone. So